Hey guys, my name is Angel, and today I'm going to be taking you through my mental process on solving the unknown problems we've been looking over in class. I apologize in advance if I have to take some time to think. This is my first time doing this, and so it's a learning process for myself. So we're going to do unknown F from the review session that they had this Tuesday. And the very first thing we're going to want to do on any of these problems is find our elements of unsaturation, find our EU. And the way that I do the EU equation is I'm going to take 2C plus 2 as a whole value minus your hydrogens divided by 2. Nitrogens are going to act as carbons, and halogens are going to subtract as hydrogens. In this case, we don't have any nitrogens or halogens, so we will continue on with our hydrocarbons. So in this case, EU would be equal to 2 times 6 carbons plus 2. We're going to do minus 10, sorry about the lack of space, divided by 2. So 2 times 6, 12, plus 2, 14, minus 10, 4. 4 divided by 2 is 2. So all in all, our EU will be equal to 2. So our elements of unsaturation are equal to 2. This is less than 4, and the number 4 on elements of unsaturation is important because it's an indication that we may have a benzene ring in the equation. So since we are not at 4, then we can rule out the idea of a benzene ring. So we're going to be looking at double bonds and rings as a possibility of our compound structure. So that's going to be the first thing we want to do, is we want to look for our EUs. And here at about 1700, you have the spectra of double bonds. So this could be a double bonded C, double bonded O's. So we'll keep that in mind. There's no N, so we won't be a double bonded N, but that also would exist in about that range. Another thing here, looking at the spectra, is we have a hydroxide group. Whenever you see this band here, kind of looks like a tongue maybe, then that's gonna be an indication that you're gonna have a hydroxide group present in the compound. Well, if you have a hydroxide and the possibility of a C double bonded O, this could be an indication that we have carboxylic acid in our equation. So we'll take a look around at the H NMR, a proton NMR, to look for that carboxylic acid. And sure enough, all the way at about 12 and past is going to be our carboxylic acid. And whenever you see this word exchange, that is going to be reassuring that we have a carboxylic acid in the equation, in the compound. So one thing I want you to notice here, though, is we have 2 H's here, and a carboxylic acid only contains 1 H. So what does that mean? This means that this is an indication of 2 carboxylic acids within the equation. And so we just found both our elements of unsaturation. We found both our double bonds. So now we have 2 pieces of our puzzle, and we're going to go ahead and put our pieces right here where we have a little bit more space. So we have 2 times the carboxylic acid. All right. So that leaves us with only hydrocarbons left, and we're going to continue by looking still at the H NMR and the possibility of hydrocarbons that we have. So we'll start with this 6H up here, which a 6H is going to be either 3 times CH2 or 2 times CH3. Okay. So the second property of this line here, this peak, is that it's a doublet. So what does that mean? That means that N plus 1 is equal to 2. And the N is going to be the number of hydrogens on the surrounding carbons. So, as an example, and this is only an example, it's not working towards our structure. Let's say we had this CH2 as the 6H, as those 3 CH2s. So we have our C with 2 H's. What this doublet here would mean is that the surrounding carbons are going to only have 1 hydrogen. So a carbon can contain 4 bonds. So we'll throw on the bonds on there. But from that doublet knowledge that we have there, we know that there will only be 1 hydrogen on the surrounding carbons, meaning that these remaining bonds all have to be either another carbon, halogens, oxygens, double bonds, but they cannot be other hydrogens, or we would see an increase in splitting. We'd see triplets and quartets. And the same goes for, one second. The same will go for the CH3s. So we have CH3 would have a carbon, and that carbon with 3 other bonds can only hold 1 hydrogen, meaning that the other 2 bonds, again, have to be either halogens or other carbons because of the doublet. So that doublet would be an indication that our surrounding carbon, in this case just 1 carbon, will only have 1 hydrogen. And so that is what the splitting is going to help us acknowledge. So now let's take a look at our 2H down here. So it can be easy to hop to a conclusion that we have just CH2, but 2H is also might be an addition of 2 CHs. And the second characteristic to those CHs is that we have, or that CH2 is that we have a quartet, meaning that our surrounding carbons are going to have a total of 3. So again, we'll do the splitting. So we have n plus 1 equals quartet 4, meaning that our n, our surrounding number of hydrogens, are going to be 3. So if we did an example with CH2, this means that the surrounding carbons, if there are 2, there may only be 1, can only have a total of 3 hydrogens attached. So we can put 1 here, let's put 2 here, another one on this end, and these must be either carbons or halogens or oxygens, anything besides a hydrogen. And these hydrogens can be arranged in all different sorts of ways. There could be 1 here, there could be 3 here, with 0 on the other side, so on, so on. So now I hope that helps you guys in the hydrogen splitting. So now what we want to look at is we need to rule out which of these carbons are not going to help. And that's going to be able to be done by looking again at the hydrogen splitting. We've acknowledged that one is a doublet while the other is a quartet. So that means that this 2H here is going to be attached to those CH3s, because if they were attached to the CH2s up here, we would get a triplet, but we have a quartet. So I'll go ahead and draw that out. If we have the CH with a carbon with 3 hydrogens on it, you know what, I'll actually do that in the purple color to represent that we will be looking at the other hydrogen, at the other carbon here. Then this works for our splitting. This works as a quartet because we have 1, 2, 3 hydrogens. And then these bonds must belong to carbons. So now we can rule out the CH2 and the 3 CH2s here. And we have all of our pieces, because now we have 2 carboxylic acids, which counts for 2 carbons. We have 2 CH2s, 2 CHs, and 2 CH3s. And so we have all of our carbons. We have 2, 4, 6 carbons. We have 4 hydrogens, and we have 1, 2, 5 times 2, 10 hydrogens, which accounts for our molecular formula. So we have all our pieces, now let's put them together. And one thing about carboxylic acids is that they will always be terminal. What do I mean by that? If they are on a ring, they are terminal. There is no possible addition to another carbon because all of the bonds have been used. And they don't necessarily have to be on a ring, they could be on the terminal end of hydrocarbons, so they could exist like this, but nothing else will be added. So in this case, where we have ruled out rings because we used our elements of unsaturation on the carboxylic acid, we now can determine that we're going to have our carboxylic acids as the terminal ends of our compound, and the remaining hydrogens and carbons are going to be within the boundaries of the carboxylic acids. So, let's start with just throwing in a CH. So those CHs we agreed are connected to CH3s. So now we want to see how are all the pieces connected. We've determined that the CHs, the CH and the CH3s are connected. So how do they connect to the carboxylic acid? Well, the only way for them to connect is through connections on like that, because you aren't going to make any connection on this C or this C because they have all their connections used, and the only available connections are on the CH, the pink CHs. And so now we've actually discovered our compound, but we want to just double check everything. So the way we want to double check is through using the carbon NMR. The carbon NMR is going to allow us to determine symmetry and the number of type of carbons that we have. And so in this case, we have 3 different types of carbon. And if we look at our compound, we actually see that we have 2 carboxylic acids that are next to the same compound. So that's one type of carbon. We have CHs that are attached to the same methyl groups and carboxylic acids. So that's 2. And then finally we have methyl groups that are attached onto CHs, and that makes 3. So our symmetry works as well. And since there are 3 carbons and a total of 3 different types of carbons, and a total of 6 carbons in the molecular formula, that is also an indication that we will have symmetry. So one thing I need to point out here, though, is you would expect this carbon here in the center. Let me see if I can, there we go, remove those. We have this carbon here. We saw that on the H NMR, it's represented as a quartet, meaning that it has 3 hydrogens next to the 3 hydrogens on the surrounding carbons, which we have here, those 3 hydrogens. However, we also have hydrogens here that belong to a surrounding carbon. But that would mean we have a total of 4, and we would see a pentet. But however, that doesn't show up because of the symmetry. So another way to look at this compound, since it is on a single bond, it can actually rotate. So here's our methyl groups, and then our carboxylic acids, you guys will just imagine those. So since it's on a single bond, it has the ability to rotate, which is going to cause these hydrogens to interact and not split because of the symmetry. They're both attached onto the same methyl groups and the same carboxylic acid groups, which makes them symmetrical. Those hydrogens have an equal amount of interaction upon another and causes them not to split. So if we did see that hydrogen in there, if we did see it on the HNMR, we would see it as a singlet. However, it's not necessary. We see it as a triplet because of the surrounding hydrogens here. We see it as a quartet. So I hope that helped you guys out. If you have any questions, please feel free to email me. I'll go ahead and write down my email. I would be glad to work on problems and send out videos to you. Any help that I can give you, I would be glad to do so. So I hope that this was a learning experience for you, and it definitely helped me out. I look forward to doing some more review videos. And good luck on your finals, guys.